So, namaskar to all IMPians and a very warm welcome to all the participants who are a part of this intellectual session today. Friends, in IMP, we have started Virtual Academy in which all the experienced people of the industry, of the energy industries, give their experience and share their technical knowledge with us. And it's a very great platform for us to learn. And friends, I, Poonam Dogra, Secretary IMP Delhi, is your host for today's session. So, friends, without much time, let us introduce you to our today's technical expert, is Dr. Rajendra Singh sir. He is a professor at Pusa Institute of Technology, which is now known as DSEU, Delhi Skill and Entrepreneurship University, in Mechanical Department. He has done his doctorate PhD in refrigeration from Delhi College of Engineering in 2015. He has a vast experience of 34 years in refrigeration and air conditioning field. Dr. Rajendra Singh Ji is, is selected as Distinguished Lecturer of ASHRAE, the American Society of Heating, Refrigeration and Air Conditioning Engineers. Not only this, he is the past president of chapter. He is a certified energy auditor and he is awarded with first position in innovation in refrigeration and air conditioning category in the 7th Bray Air Award for Excellence in HVAC and Refrigeration. And he has two patents. First one, efficient split desert cooler, and second one is scrapped surface ice slurry generator.
Poonam ma'am. Now, I am good evening to Mr. Sood Saab, Mr. Bibu Sawarn Saab, and other IMP senior members, consultants, and our ASHRAE side, Abid Hussain sir, Kanak Raj sir, and our ASHRAE members, Ranjit and Indrani, etc. Basically, I am a live member of IAEMP, and I cleared my energy editor exam in the year 2010. And I am a live member of ISHRAE, live member of ASHRAE India chapter, and distinguished lecturer ASHRAE USA. And my aim is to distribute my knowledge, my level of knowledge to the students, to the industrial people. And I think no one is perfect. Everyone having a knowledge level, and according to his level, he can teach, he can distribute the knowledge, and also upgrade his knowledge level. This knowledge is a learning process. It is continual learning process. Now, in future, I will now I am chair student activity Asia India chapter, and I found many. Now today my topic that is related to the refrigerant, that is country refrigerant. First, I discuss with 5 minutes some important terms in our basic terms that each and every engineer, each and every energy editor must know that things to understand this topic. Now, number one is what is temperature? All of you aware, in the normal definition, the temperature is the degree of hardness and coldness, hotness and coldness. This is a very old definition. Now, according to my new definition, the temperature is a thermal potential of a thermodynamic system. For example, in our houses, we are having the water tank, and the water tank is normally on the rooftop level, and the tap that is on the bottom level. When we open the tap, the water is flowing through the tap. This means water is flowing due to the level difference in the tank and the tap. That is why water is flowing. This is known as head. I think all of our participants, they are aware. Okay? Like that, energy flowing. For example, you took a spoon and you switch on the gas stove, put the one end of the spoon to the flame of the gas, the flame, and after some time, you feel hot on the other side. This means heat is transferred from high temperature to low temperature, from high thermal potential to low thermal potential. So this means temperature is the thermal potential of a thermodynamic system. Like that, heat, all of you aware, heat is a form of energy that flows due to temperature difference. There are two types of heats. One is the sensible heat, other is the latent heat. So in sensible heat, we took an example in our houses. We are preparing the tea. We are taking water in a container and we switch on the gas stove. Suppose initial temperature of the water is the surrounding temperature, environment temperature. For example, temperature is 35 degree. We switch on the gas. We are heating the water. We are giving the heat to the water. Temperature is increasing from 35 to 40 degree, 50 degree, 60 degree, 70 degree. What is the meaning of this? We are adding the heat to the water. This heat added to the water is known as sensible heat. Now, what is the definition of sensible heat? The amount of heat required to change the temperature of a thermodynamic system without changing its state. The state is same, that is water. This is sensible heat. Now, second is the latent heat. Now, what is latent heat? Further, we are heating the water, temperature increasing from 70, 80, 90, 100 degrees C. In the normal atmospheric pressure, at 100 degrees C, water starts boiling. This means changing the state of water from liquid state to the vapor state. Now, at this state, the amount of heat added is known as latent heat. Now, we'll form the definition. The amount of heat required to change the state or phase of a thermodynamic system without changing its temperature. We assuming theoretically temperature remains constant, but practically there is a small variation in the temperature. So like these are the some fundamental definitions. Latent heat of various types, latent heat of vaporization, state change from the liquid to vapor, latent heat of condensation, state change from the liquid to the from vapor to the liquid, and latent heat of freezing, state change from liquid to the solid ice, then latent heat of melting or fusion from solid ice to the liquid water, and the last is latent heat of sublimation. All of you aware, the state change directly from the solid state to the vapor state. There is no liquid state in between. For example, camphor, dry ice, many more examples you see in the daily life. These are the definition that we have to use in our heat transfer, thermodynamics, energy audit. We must know these things. Now, I am sharing slide.
Yes, sir.
Visible to all?
Yes.
Very good. Now, today our topic is use of green secondary refrigerant, that is known as ice slurry for refrigeration and air conditioning. Now, first, you must understand this secondary refrigerant. I am taking an example of a central air conditioning plant. For example, there is a building, shopping mall building, or hotel building, or any hospital building, office building. In the normal practice, you find central AC plant. In central AC plant, what we are doing, we are producing chilled water and flowing the chilled water through the chilled water pump, chilled water pipeline to the air handling unit and fan coil unit. And these AHU and FCU, they are cooling the air, and through duct, we are supplying the air, the areas we have to air condition. So this known as primary refrigerant. Now here we are normally using in our central AC plant chilled water. Chilled water is cooled by the primary refrigerant, either this R134A, and to design some system that are leak proof. Small quantity of refrigerant used and leak proof systems should be there, and less amount of refrigerant going to the atmosphere. Third is to increase the efficiency of our vapor compression system. So these are the various ways we have to use to minimize these problems. Now, as I explained you, when we are using water in our central air conditioning plant as a secondary refrigerant. Now, this water application is only limited to the air conditioning. But why we have to do for the refrigeration purpose? In refrigeration purpose, if we want to use water as a secondary refrigerant, now below 0 degree, water start freezing. So we cannot use water as a secondary refrigerant in our refrigeration system. So that is the limitation for only air conditioning systems. Now the alternative is ice slurry. Now we come to our topic, ice slurry technology. Okay. Now we understand what is ice slurry. Now this ice slurry is a homogeneous mixture of small particles. The size is 0.1 millimeter diameter to 1 millimeter diameter, very small size diameter, and a carrier fluid. For example, pure water and freezing point depressant. These are also known as antifreezes. I think some people they know that. प्योर वाटर एंड फ्रीजिंग पॉइंट डिप्रेजेंट, दूसरा नाम इसका एंटी फ्रीज. तो ये एग्जांपल है लाइक सोडियम क्लोराइड, इथेनॉल हो गया, इथाइलिन ग्लाइकोल हो गया, प्रोपिलिन ग्लाइकोल हो गया. दीज आर द सम ऑफ द डिप्रेसेंट वी आर यूजिंग. आपको पता ही होगा इन अवर आइस प्लांट के अंदर क्या होता है, आइस टैंक होता है, फ्रीजिंग टैंक. नॉर्मली वी आर यूजिंग सोडियम क्लोराइड solution as a secondary refrigerant or calcium chloride as a secondary refrigerant. So this is ice slurry. Ice slurry having a small ice particles, solid particles in liquid. So what is the meaning of this? In liquid we are having solid. So we are having double effect. One is the sensible heat removal. Second effect is the small solid ice particles. When they melting, they transfer the heat. We are getting the latent heat effect. So that is why our heat transfer rate, heat transfer coefficient, that will increase due to this mixture of liquid and small solid crystals. So this is the definition of the ice slurry that we can use instead of this chilled water. अब आप देखिए कि what are the various features of ice slurry. क्या क्या बेनिफिट हैं आइस स्लरी के. तो आइस स्लरी हैविंग ए फ्रीजिंग पॉइंट डिप्रेसेंट. तो फ्रीजिंग पॉइंट काफी कम कर सकते हैं. इन माय एक्सपेरिमेंट्स बाय यूजिंग वेरियस डिप्रेसेंट्स आई अचीव्ड -25 degree C temperature in the ice slurry system. Okay, and this ice slurry having better transport properties in tubes, pipes and heat exchangers. In my practical experiments, I flow the ice slurry through the pumps, through the heat exchangers. I used plate heat exchanger. I hope some of you know what is the PHE, plate heat exchanger. That is having a very small hydraulic diameter of the order of 4 millimeter. So I pass the ice slurry through this small size heat exchanger, and I got the very good results. अब आगे देखिए आप, reduction in tube or pipe size. Instead of chilled water, if we using the ice slurry water, so ice slurry having a liquid plus solid ice crystals. So this means solid occupying less space. The specific volume of the gas is more. The specific volume of the liquid is less than the specific volume of the gas. The specific volume of the solid ice is less than the specific volume of the liquid water. So this means by this mixture, the specific volume of the overall mixture that is reduced, and in comparison to the chilled water, we can use the small diameter pipes as compared to the pipe used in the chilled water system. So this means small diameter size pipe are used our cost of the installation that will reduce by using ice slurry. The next is the reduction in the energy consumption. I already explained due to the double benefit. One is the sensible heat transfer, second is the latent heat transfer. मैंने आपको sensible और latent heat की definition इसलिए बताई कि you must understand what is sensible heat and what is latent heat. तो यहाँ पे हमें दोनों चीजें मिल रही हैं, तो उससे हमें क्या होगा, रिडक्शन इन द एनर्जी कंजम्पशन. तो हमारी जो एनर्जी है दैट विल सेव बाय यूजिंग दिस टू फेज फ्लो. Chilled water is a single phase fluid. Now ice slurry is a two phase fluid, liquid plus solid crystals. Now if we using ice slurry, the heat transfer coefficient that will increase. This is also very important. In my design, in my experiments, I calculated the heat transfer coefficient that increased. And as you aware, the Newton's law of cooling or heating, in the heat transfer in convection mode, the heat transfer is directly proportional to the temperature difference multiplied by the heat transfer coefficient. If this heat transfer coefficient small h will increase, the Q value increased. So that is why we are getting high heat transfer rate as compared to the chilled water. And by this we are saving energy. Now next is the environment friendly technology. This is very environment friendly. Why? Now for producing ice slurry, we need a very small system. A small amount of refrigerant is used. And we are preparing the ice slurry and we are storing in the thermal storage insulated tanks. And through these thermal storage tanks, we can pump the ice slurry to the applications where we required. Now, better peak load performance. This is very, very important in any nation. For example, in peak summer, the ambient temperature is around 44, 45 degrees C normally. And the electricity demand is very high in the peak summer. And sometimes what happens, due to the heavy load on our grid sometimes trips. Now what we will do, we will produce the ice slurry in the off-peak hours. We can produce the ice slurry in the night hours. We can store the ice slurry and we can use in the day when the demand is very high. By this, we can reduce the load on our grid and there will be no chance of tripping of the grid. So that is very important feature of the ice slurry in the thermal storage system. That is very, very important. So I hope you know the various benefits of ice slurry. Now I change the slide. Now applications of ice slurry. Ice slurry having number of applications, starting with the comfort cooling. In air conditioning, we can use ice slurry. Commercial refrigeration and industrial production processes. In refrigeration, normally we need around 2 to 8 degree for the fruit and vegetables, and below 0 degree in our frozen items like minus 10 degree, minus 20 degree C temperature for frozen meat products, ice cream, and frozen butter, etc. Then next is the milk production. In milk plant, we can also use ice slurry. Mine cooling, where mine process is going on. For mine cooling, we can install the ice slurry system for the cooling purpose. Then food processing and preservation, that is also important. These days in our cold chain, we are focused on the food processing and preservation. Then next is the fish processing and fish freezing. For example, you want to freeze the fish. Now, you can directly quench the fish in the ice slurry tank of a low temperature, around minus 20 or minus 25 degrees C ice slurry temperature. After some time, you found this oil, this fish will be frozen. So that we can directly do in the ice slurry tank. Many more applications like we can use in the medical line, medical research line, firefighting also. Oil, ice pigging means for the cleaning of the various pipelines, we can use the ice slurry. Artificial snow, for producing artificial snow, we can use ice slurry. Transport applications. For example, in our cold chain concept, we need refrigerated vans, we need refrigerated trucks. So we can use ice slurry. We can flow the ice slurry in the cooling coils of the tanks, and we can use in the transport applications. For that, we need pumps, like petrol pumps. We need ice slurry pumps. From on the way, on the roadside, we need like this. And when ice slurry finished in that system, before before that, they can fill the ice slurry tank in the transport also. So in future, we can do many things by using this ice slurry and take the benefit. In my experimental work, initially I designed a prototype, a small size 5-liter capacity ice slurry machine. I designed, then manufactured in the small scale industry level. And in the third stage, I analyzed the ice slurry, and I took the data of the ice slurry, and I proved the saving in the energy. And in the second stage, I designed a medium size 74-liter capacity ice slurry machine, and also manufacture of this machine, and the various experiment using the data logging system and laptop, the each and every reading that comes out on my laptop, and I recorded the readings. I I made the theoretical model also in programming, and second I done the experimentally, and last I compared theoretical data with the experiment data, and that approximately match, and that proves ice slurry is a very good secondary refrigerant for the future. So these two machines I developed, and this medium-sized machine that is installed in the Delhi College of Engineering Research Lab, and that is having the complete system: ice slurry machine, and ice slurry storage tank, chilled water tank, then normal water tank, plate heat exchanger, and various pipelines, various pumps. And in my experiment, I initially use the chilled water, and I done experiment with the chilled water and normal water, and in the second stage I use the ice slurry versus normal water, and by comparing that I proved my results. So I show you on my later slides various graphs and results I achieved. Now this is the vapor compression cycle of the ice slurry system. All of you aware, in our vapor compression cycle, we are having four major components: compressor, condenser, throttle device, and evaporator. Here, evaporator is the ice slurry machine. This is the pressure enthalpy diagram, as you all you aware. 1 to 2 is the compression, condensation, throttling, and evaporation. So this is basically the vapor compression cycle is used for this system. Now this is the photograph of my small size machine. Now you see here, this is the ice slurry machine. These are the various sensors to take the temperature and pressure readings. And this is the ice slurry tank. This is the condensing unit of the system. So this is a small machine I developed. You see the photograph of the ice slurry having crystals. These crystals are used in the chilled water. Now these are the various components that I used: compressor, condenser, the expansion device. In the small machine I used capillary tube, evaporator, and these are the various components of the ice slurry system. Okay, this is the medium size ice slurry. Now this is the ice slurry generator that I designed. This is the motor for use by the ice slurry generator. This is the solution tank. This is the antifreeze solution tank. This is the ice slurry tank, and below this is the condensing unit and fans. And this is the rotameter. All of you aware, rotameter is used to measure the flow rate. Okay, so this is the photograph of my medium size ice slurry machine. You see here, this is the ice slurry produced, and this ice slurry is flowable, pumpable from the tank. You see, this is easily flowing, and this is a mixture of chilled water and very small crystals from 0.1 to 1 millimeter. We are taking the latent heat effect by these crystals. Now this is the measurement of the crystal size with the instrument. In my experiments, I use the various percentage of these antifreezes like PG and MEG in the small machine in the ratio of 10%, 20%, and 30% solution. In the medium machine, I used PG, MEG, and DEG, three depressants in the percentage of 10%, 20, 30, and 40%. So these are the various percentage used in the various experiments. Now these are the specification of the medium size of the machine I used. Now this is important. These are the various measured thermodynamic properties using MEG as a antifreeze. Now in this, I took the various parameters like compressor suction, compressor discharge, condenser inlet, condenser outlet, and after expansion, pressures as well as temperatures. By using these, I done the calculations and I calculated the first law of thermodynamics. I calculated the COP of the system, coefficient of performance. I think all of you are aware what is the coefficient of performance of the vapor compression cycle. It is the ratio of net cooling effect divided by work required in the compressor. So these are the various instruments I used in my experimental work. First is the mass flow meter. These are the specifications and accuracy of the mass flow meter. Now, this mass flow meter is a very important mass flow meter, not a normal mass flow meter. In this mass flow meter used for the two-phase flow. In normal practice, we are using single type of liquid, only single mass flow. This is special mass flow that is measuring the mixture of liquid and solid particles. Then differential pressure transmitters using the pressure difference between the 2 points of the plate heat exchanger, various pressure transmitters, and RTT for the temperature measurement. These are the range of the RTT and these are the accuracies of the various instruments. And I use a data logger DT822 having 16 terminals with the accuracy of 0.01% in my experimental work. Now these are the measured thermodynamic properties in the medium size machine using the propylene glycol as an antifreeze. So you see here compressor suction pressure and temperature, compressor discharge, condenser in, condenser out, and after expansion and ice slurry temperature. Next is the ice slurry temperature. So you see in this from 10, 20, 30, and 40%, from -5.7 to minus 20.7 minimum temperature by using propylene glycol as antifreeze. By using MEG, MEG as a glycol, I achieved minus 25-degree temperature. Okay. Now this is the heat and work calculation of the COP of the system. In this, you see the refrigerant effect at various percentage 10, 20, 30 in the small machine. So this is the net refrigerating effect calculated by using the pressure enthalpy chart and temperatures. Then compressor work required in the compressor by enthalpy difference, and then calculation of the coefficient of performance. So this is the various coefficient of performance by using various percentages, and heat rejection ratio also calculated at various percentages. Okay. Now these are the graphs showing the freezing temperature versus the time for propylene glycol of 10%. Here propylene glycol of 20%. These are on the x-axis time is there, and on the y-axis temperature is there. So you see here the various points are ice slurry temperature, then refrigerant temperature at evaporator inlet, refrigerant temperature at evaporator outlet, and refrigerant temperature at condenser in and condenser out. So these are the various parameters at the in the graph form. From table to I converted into the graphical form. Okay, and these are the stages from T0 to T1, T1 to T2, T2 to TF. I show you the three stages in the next slide. You see here. Now stage 1 is known as cool down period. Initially, when we start the auxiliary machine, we are using the water and mixture of water and depressant. Starting it is cool down, and there is a temperature difference T0 to T1. In the next stage, nucleation period. Now what is happening in the nucleation period? The ice seeds formation is there after the supercooling. Then more cooling is there, and small ice seeds are start forming, and this volume is increasing as the time is increasing. Okay, and this is known as nucleation of the ice particle occurs. In the third stage, ice slurry generation period from T2 to T final. So full-fledged ice slurry formation is there in the third stage. So that is shown in the graph, and these are the meaning of the various T0 to T1, T1 to T2, and T2 to the T final stage. Here we got the ice slurry. Now this graph showing the volumetric ice concentration versus the time for the one depressant, PG depressant. So you easily see here on the y-axis, that is the volumetric concentration, and on the x-axis, this is the time period. Okay, time in minutes. So you see in the graph, as time is increasing, our machine is starting, time is increasing. You see here the volumetric ice slurry formation, seed formation is there. Then ice slurry concentration is increasing. Concentration is increasing as time is increasing up to here. This is around 50%. So at 50%, this is constant for some time. So normally for our application, the 50% concentration is more than sufficient to achieve the good results. So that is our final stage of the ice slurry production. Now this is the achievement by using these antifreezes. This is the case of the medium-sized machine of 74-liter capacity by using PG, MEG, and DEG. You see the range of temperature we achieved from 10, 20, 30, and 40%. Temperature by using PG is minus 5.7, minus 10.2, minus 15.3, and maximum minus 20.7 at 40% of the depressant. In case of MEG, the maximum temperature is achieved around minus 25.6 degrees C. This is more than sufficient we can use in our refrigeration purpose, used for the freezing purpose in refrigeration also. And in DEG, this is slightly less. Maximum temperature is minus 19.9 degree Celsius, degree C, I didn't mention. Okay, so these are the various temperatures achieved in the ice slurry machine. Now this is a graph showing good results. Freezing, this is the freezing curve. Now on the x-axis, anti-freezes mass fraction is there, and on the y-axis, freezing temperature is there. So you see here, when the ice slurry mass fraction increasing 10%, 20%, 30%, 40%, as you see in the result table. Okay, so graph is showing also this. So as the mass fraction is increasing, the temperature is reducing. So we are having minimum temperature here for PG, MEG, and DEG. So this is the graphical representation of this table. Okay. Now next, this is the COP calculation of the medium size machine. We calculated the net refrigerating effect at various percentages, 10, 20, 30, and 40%. Then work required in the compressor and coefficient of performance, heat rejection in the condenser. So these are the various parameters, the actual parameters, and after calculation, we achieved the value of the COP at various percentages. So you see here, as the temperature is reducing, the COP is slightly reducing. At minimum temperature, COP is slightly less as compared to at this temperature. So this is the fundamental of all of the refrigeration engineers. They know about that. Now this is the thermodynamic properties of the ice slurry. So this was very typical to calculate the thermodynamic properties, because this is the two-phase flow, and for calculation many more formulas are to use to calculate the various parameters. In my heat transfer calculation, it took around 6 months to decide the final formula for two-phase flow. It is not a simple task for the two-phase flow design. Single phase flow design is very, very simple if we are using chilled water. But if fluid is two-phase flow, then it is very difficult to design. So these parameters we calculated: temperature, density at various percentages, dynamic viscosity, thermal conductivity, and specific heat, and then Prandtl number. So these are the various calculations done in the experiments. Now in the final stage, in the last stage, in the experimental stage, this ice slurry flow in the heat exchanger, plate heat exchanger. So all of you are aware, this is the cut view of the plate heat exchanger. These are having corrugated plates. All of you are aware, having corrugation angle. And this is a very good heat exchanger and very compact heat exchanger. These days, the chilling unit people in the plastic industry and many other industries in the chilling unit industries, people prefer this plate heat exchanger because it is a very compact and heat transfer is slightly more than the other type of heat exchangers, and it takes very small space. Space saving is there. Our system will be compact, and this PHE I used in my experimental work. Now this diagram show you the geometry of the diagram. This is the corrugation angle. This is the hydraulic diameter. This is the hydraulic diameter. That is around 4 millimeter. And through this hydraulic diameter, the ice slurry flowed to the by using the pumps. So it is very easy to flow the ice slurry through the PHE. Now these are the various specification of the PHE I used. The number of plates, the equivalent diameter, pore diameter, number of passes, and these are the various parameters: corrugation angle, plate thickness. These were used in the calculations. Now I made the thermodynamic model by using the MATLAB and using the this represent the relationship between the steam heat transfer coefficient, pressure drop, and heat exchanger area. So these three parameters are very important in the design of the mathematical model of the plate heat exchanger. And this model provides the possibility of and predict the heat transfer based on the allowable pressure drop. So by the pressure drop, we can calculate, we can predict the heat transfer coefficient. And this prediction are compared with the experimental data. And after that, I compare these parameters of my hydraulic model compared with my experimental data. Now this is the complete assembly of the ice slurry system. You see in the diagram, this is the ice slurry generator. This is the ice slurry storage tank, thermal storage tank is there. And this is the condensing unit of the ice slurry. This is the data logging system to take the data on the laptop. And you see here, this is the plate heat exchanger in which we flow the ice slurry and we took the various results. These are the various sensors, temperature sensor and pressures at in and out of the plate heat exchanger, and various other sampling points, various other valves are used, flow meters are used. So these are the various equipments, mass flow meter and other equipments used in the complete setup. So this is the complete setup of the ice slurry system. In the first phase, instead of ice slurry tank, I used one other tank, that is the chilled water tank. And in the heat exchanger, in one side, I pass the chilled water. On the other side, I pass the normal water that is having higher temperature. And I took the various data. In the second phase, I use this ice slurry to the ice slurry tank and pass through the plate heat exchanger. On the other side, I pass the normal water and I took the various data, and then finally I compared the first stage, the chilled water was versus normal water. Normal water means hot water. Second phase, the ice slurry versus the normal water, hot water. Now these are the some of the photographs of my setup, and you see here, this is the chilled water tank. This is the normal water tank known as hot water tank, and this is the plate heat exchanger. You see, and this is the flow meter, and this is the differential pressure transducer. This will give the pressure difference across the plate heat exchanger. So this setup is in the complete lab of the research lab of the DTU. Earlier that was Delhi College of Engineering. Now these are the various other components. Now this is the photograph of the chilled water system. This is the coil of the chilled water system. This is installed in the chilled water tank. This is the condensing unit by using a sealed compressor by used in the vapor compression cycle to produce the chilled water. Now see, this is the chilled water pump used. This is the electrical panel having various controls. Now this is the flow meter, mass flow meter. This is two-phase mass flow meter. This is very important component that was very costly component that we imported from the Germany. And this is the pressure transducer, differential pressure transducer we used. Now in our experiments, these are the operating parameters. First is water to water, means chilled water versus normal hot water. And in the chilled water tank, we maintain the 4 degree C temperature by using the chilling unit. And at that time, the normal water temperature was 17.4 degrees C maintained. And the mass flow rate we are changing in case of chilled water from 0.08 triple three to 0.8 triple three kg per second. And the flow rate of the normal water is fixed, that is 0.1944 kg per second. And this is the thermal conductivity of the plate material, that is 13.56 watt per meter Kelvin. So these are the various parameters used in the water to water system. Now this is the result. This graph showing the flow rate versus cooling duty, means the heat transfer we achieved, cooling we achieved. This is the case of chilled water and ice slurry using PG as an antifreeze. So in this diagram, you see this is the cooling duty, Q. And on the x-axis, this is the flow rate. I show you this is the flow rate. This is the flow rate of chilled water and ice slurry. This range at various steps. That is why we achieved the graphs. Minimum is this and maximum is this. And in second case, instead of chilled water, we use the ice slurry water. In the graph, you see this curve is, that is for the chilled water. So you see the cooling duty, that is in the lower state. In this, there are two datas. One data is for the model, the thermohydraulic model I achieved mathematically. And second is the experimental. So you see in the diagram, these two are matches nearby. These lines are nearby, you see, almost accurate. So this bottom is for the chilled water versus normal water. And this above curve for the normal water versus ice slurry. Ice slurry at 10% concentration, ice slurry at 20% concentration, ice slurry as 30% concentration, ice slurry at 40% concentration. So you see here, we are getting the more cooling effect by using the ice slurry as compared to chilled water. This graph showing experimentally as well as mathematically modeled two-way. So that is our achievement. You see in this diagram that will show how much efficient is ice slurry as compared to the chilled water. The second diagram, first diagram is for using propylene glycol as an antifreeze. In the second case, the glycol is MEG is used, and we achieved the results. This curve for chilled water versus normal water, and these four curves for the ice slurry water versus normal water, 10, 20, 30, and 40%. So these are the final results I achieved in my experiments. Now you see this graph is on the x-axis the flow rate, on the y-axis pressure drop. So as you aware, when we use thick fluid, the pressure drop is also increasing in the pipelines. Okay. But when we compare the cooling duty versus pressure drop increase, the cooling duty increase is more as compared to the pressure drop increase. So that is why it is a good to use the ice slurry, and this graph show the variation of the pressure drop versus flow rate. Now this graph showing the pressure drop versus Reynolds number. Okay, so that is slightly increasing by increasing the concentration. This is also for other refrigerant. Earlier was for PG. This is for MEG, monoethylene glycol. The second for MEG, monoethylene glycol. Now this is the result you see on the slide. Now, by using the chilled water and ice slurry as secondary fluid, performed to validate by thermohydraulic modeling for prediction of pressure drop, heat transfer coefficient in the plate heat exchanger, this is our result. The pressure drop in the ice slurry is 10 to 40%. Concentration is between 5 to 48 kilopascal at a flow rate of 0.25 to 3 meter cubic per hour, which is about 1.1 to 3 times of that of chilled water. The pressure drop was found to increase with the flow rate. So this is pressure drop. In the second, we see what is the benefit of ice slurry. In the parallel, by using the ice slurry in the plate heat exchanger, you see the results. Cooling duty of the ice slurry increasing with increase in the antifreeze concentration 10%, 20, 30, 40%. By using ice slurry in the plate heat exchanger, cooling duty found was increased by 50% at minimum flow, means 0.3 meter cubic per hour, and increasing up to 37% at the maximum flow, 3.0 meter cubic per hour, at 10% ice concentration, ice crystal concentration of PG, one example, and pressure drop increasing 10%, 0.3 meter cubic to by 7% at 3. So when we compare, the cooling duty increasing is more as compared to the pressure drop increase. So this means the ice slurry is giving very good result as compared to the chilled water system. Now these are the single graphs. We already seen these graphs for water to water, one by one. So that is overall heat transfer coefficient versus flow rate, cooling duties versus flow rate. We already seen the combined. These are at various percentages, 10, 20, 30, and 40%. So these already we know the graphs. Now these are the various achievements that achieved in my experiments. You see, now this ice slurry generator I produced by using the common used manufacturing process in a small workshop, not in a large company. At a small scale, I produced this ice slurry machine fabricated in a small scale workshop. Second, in the this medium machine, I used R410A as a refrigerant. That is refrigerant blend having zero ODP. So ODP आप देखोगे zero है. So that is a very good refrigerant that we can use, and the quantity of refrigerant used is very small, and there is no harm to the global warming also. Now, as we see in the earlier slide, there are 3 stages in the ice slurry production: cool down to chilling period, nucleation period, and then final ice slurry generation period. That are the 3 stages we achieved. And the temperature we achieved, you see, by using the various depressant, minus 5.7 to 20.7 degrees C in the case of propylene glycol at various percentages, as in case of monoethylene glycol MEG, low temperature achieved is minus 25.6 degrees C. In the DEG, the minimum temperature achieved is minus 19.9 degrees C at various concentrations. Now, in the next, the freezing temperature reduces with increase in the antifreeze mass fraction of PG, MEG, and DEG. I already show you the slide having the graph. Okay. Next is the time required for 50% measured volumetric ice concentration increases with increase in the concentration of PG, MEG, and DEG. That we also seen in the graphical form. Okay. So these are the various COP achieved at various percentages of PG, MEG, and DEG. The coefficient of performance calculated shown in the various tables. Now in plate heat exchanger, we uses chilled water versus hot water. We calculated the cooling duty. We calculated the overall heat transfer coefficient. This overall heat transfer coefficient that is increased by in the ice slurry with the flow rate. And earlier we used the ice slurry versus hot water. Now, conclusion. It can be concluded that the present formulation provides the relationship of to predict heat exchanger based on the available pressure drop and reasonably matching with the experimental data. The thermal hydraulic model is useful for the design of the PHE. So by this, my thermohydraulic diameter, if I having the pressure drop value or I having the heat transfer value, I can calculate the area of the heat transfer. In this mathematical model, I put the inputs, and by putting the inputs, I get the final design of a perfect heat exchanger. Now, this this model, mathematical model, can be extended for the optimization of the plate heat exchanger networks. So we can also optimize the heat exchanger by using the mathematical model of the heat exchanger design also. Now, these are the various references, various research papers I studied in my research work. Some of the research papers are shown there. There are a number of papers. In the more than 100 papers I read for this design. These are some of the papers. Now, number of papers published in the international journals and number of research papers I presented in the various conferences. Recently, I presented in a conference in USA in 2018, and now one of my paper is selected by a conference in Canada on 26th of June, and I am trying for NOC and I am trying for the visa. So I hope I will go to Canada to present this research paper. These are the awards. Now, this award is given by the Braille Asia company on this research work. They have given me the trophy as well as at 1 lakh rupees check for the best innovation in India in this ice slurry system. And this award I get in the international conference to be held in the Jamia Millia University on my presentation of my research paper on this topic. Now, two patents are granted and some more patents that are in pipeline. This first is the efficient split cooler that is granted by Indian Patent Act Office. Second is the ice machine that is also patented. Now, thank you to all of you for patiently joining the workshop seminar.
Seminar.
Hope you understand
Hope
the
you understand the
auxiliary system